Hey everyone, and welcome back to another explainer. If you're a focused learner looking to completely master the inner workings of computer processors, well, you are in exactly the right place. Today, we're bringing some serious energy to a high-yield exam revision session. We are going to unpack the absolute core of computing power, looking at exactly how processors are designed, how they differ, and how they team up to tackle massive tasks. Let's get into it.
All right, let's just quickly glance at today's roadmap. 1. The quest for speed. 2. RISC versus CISC. 3. Multicore and parallel systems. 4. Types of parallel processing. And finally, 5. The exam summary.
Starting right off with Section 1, the quest for speed, overcoming the von Neumann bottleneck.
So it literally all starts with this one massive question. How do we actually make computers faster? And the answer is always a bit of a delicate balancing act. We essentially have two options. We either optimize the software, so it asks the computer to do less work, or we expand the physical hardware so it can process way more work in the exact same amount of time.
Okay, to really get processor architecture, you absolutely have to wrap your head around the fundamental CPU time equation. Basically, total CPU time equals the number of instructions times the average clock cycles per instruction times the seconds per cycle. So think about it. If we want to speed up the CPU, which means we want to reduce that total CPU time, we logically have two main choices. We either have to reduce the number of instructions the program actually needs to run, or we have to reduce the average number of clock cycles that each of those instructions takes. Keep this equation in the back of your mind, because it is literally the entire basis for the two totally different design philosophies we're about to explore.
Moving right along to Section 2, RISC versus CISC, two competing philosophies of processor design.
Right, so these are basically our two primary architectural solutions to that speed equation we just looked at. On one side, we've got RISC, which stands for Reduced Instruction Set Computer. RISC attacks the equation by aggressively reducing the average clock cycles per instruction. Then on the other side, we have CISC, or Complex Instruction Set Computer. CISC attacks the totally opposite part of the equation by trying to reduce the total number of instructions per program. They both desperately want the same thing, faster execution, but man, they take completely different paths to get there.
Let's zoom in on RISC first. RISC architectures support a relatively small number of really simple instructions. Think of it like a super efficient fast food assembly line. Every single step is incredibly simple, taking exactly one clock cycle to complete. Now, because the steps are so small, you obviously need more of them to get the whole job done. That means writing more lines of code, which inevitably places a heavier burden on your software and your RAM. But to keep this fast-paced assembly line humming without constantly waiting for slower main memory, RISC architectures require a ton of internal registers for extremely fast data access. Oh, and this is crucial. Only specific load and store instructions are allowed to actually access memory directly.
Okay, now let's totally flip the script and look at CISCs. If RISC is that fast food assembly line, CISC is more like a master chef working completely alone in a high-end kitchen, just doing all the incredibly complicated prep work themselves. CISC architectures support a huge number of complicated instructions. In fact, a single CISC construction might actually be made up of a bunch of smaller, RISC-type instructions happening behind the scenes. Because of this, one instruction takes many clock cycles to complete. But the huge trade-off here is that because the hardware is doing the heavy lifting, you need way fewer lines of code in your program. It gives you a bunch of different addressing modes, and unlike RISC, many different types of instructions can access memory directly. Historically speaking, this made writing in assembly language so much easier for programmers.
So for a long time, we just tweaked architectures back and forth between RISC and CISC, or we just kept packing more and more transistors onto our chips. Moore's Law style, doubling the transistors every couple of years. But eventually you really have to ask, what happens when we literally hit a physical wall? What do we do when we simply cannot squeeze a single extra transistor onto a silicon chip without the whole thing just melting down?
Which brings us nicely to Section 3, Multicore and Parallel systems, hitting the wall and teaming up.
All right, definitely grab a pen for this one because it is highly testable and perfect for your flashcards. A multi-core system is a computer architecture where the CPU has more than one independent processing unit, which we call a core. These cores exist right there on the exact same physical chip, but they can run multiple separate processes concurrently. It's essentially the physical hardware solution to hitting that performance plateau we just talked about. But hardware is really only half the battle, right? We also have parallel processing. This is when two or more processors actually team up to perform a single task by chopping it into smaller subtasks or threads.
Those threads are then executed simultaneously by all the available processors. But here is the major catch. Your software actually has to be specially written to take advantage of this. It's kind of like coordinating a massive crew of construction workers building a house. If you don't give them clear, separate tasks that can be worked on at the exact same time, they're just going to bump into each other and probably slow the whole build down.
Let's dive into Section 4, Types of Parallel Processing, the Parallel Playbook.
So we generally drop parallel computing systems into one of three buckets. First up is MISD, Multiple Instruction, Single Data. This is where multiple processors apply entirely different instructions to the exact same set of data. Next is SIMD, Single Instruction, Multiple Data. Here, your multiple processors are all following the exact same set of instructions, the same algorithm, but they're applying it to lots of different data concurrently. Finally, we have MIMD, Multiple Instruction, Multiple Data. In this setup, multiple processors can actually process completely different instructions on completely different data simultaneously. MIMD is absolutely the heavy hitter today. It's the architecture running everything from your desktop PC to those massive room-sized supercomputers forecasting global weather.
Okay, let's talk trade-offs, because obviously nothing is perfect. The advantages are pretty fantastic. You get way more jobs done in a much shorter time because everything is happening simultaneously. And tasks are shared to reduce the load on individual processors, which totally avoids bottlenecks. But consider the downsides. It is notoriously difficult to write programs for multi-core systems. You have to be super careful to ensure each specific task gets the correct input data. On top of that, all those results from the different processors need to be stitched back together at the end. That's a really complex process that actually adds to your total execution time. And fundamentally, not all tasks can even be split across multiple processors. Some things just logically have to be done one step at a time.
Wrapping up with Section 5, the exam summary, high-yield revision takeaways.
Let's rapid-fire recap the 4 huge pillars you absolutely need to lock in. Number 1, the CPU time equation totally dictates performance. Remember, it's all about managing those instructions and cycles. Number 2, RISC goes for speed by using simple instructions completed in just one cycle, while CISC uses super complex instructions that take many cycles but use way less code. Number 3, when single processors hit their absolute limits, multi-core systems use multiple physical cores and parallel systems step in to split single tasks across them. And finally, number 4, parallel processing offers massive speed and shared loads, but that comes with a pretty heavy cost of incredibly complex software development and the annoying overhead of combining all your final results.
Before we wrap this explainer, I want to leave you with a bit of a provocative thought. We know hardware folks can just keep slapping more and more cores onto chips, creating these massive multi-core behemoths. But concurrent thinking, that actual human skill of recognizing which parts of a problem can be solved at the exact same time, is insanely complex. As we start relying on parallel processing for literally everything, from running sprawling game servers to crunching petabytes of big data, will our software development and our actual algorithms truly be able to keep pace with our crazy hardware? Honestly, it's the ultimate challenge for the next generation of computer scientists. Thank you so much for joining me for this explainer. Keep up the fantastic studying, and I'll catch you next time.